Imagine this. Millions gaze at the night sky and witness an anomaly, a point of light from another star system, defying expectations. On December 19th, 2025, an object named 3I Atlas will make its closest approach to Earth, raising unanswered questions. Is it merely a comet or something more extraordinary? This moment, which could redefine our understanding of the universe, is fast approaching. So before we go deeper, hit like, subscribe, and tell me in the comments what you think this really means. And if you want to help this message reach others who still wonder, share it. On X, Facebook, Reddit, or even just in your group chats. You're the reason this search is alive. Thank you for keeping your eyes open. Detected in 2022 by the Pan-STARRS telescope in Hawaii, 3I Atlas has puzzled astronomers with its unusual behavior. Its trajectory suggests it is an interstellar traveler, journeying through the cosmos for eons. If confirmed, it would join Oumuamua 2017 and Borisov 2019 as only the third interstellar object ever detected. However, 3I Atlas will pass within 0.25 astronomical units of Earth, an unprecedented proximity for such a visitor. This closeness offers scientists an unparalleled opportunity. Telescopes like Hubble and James Webb will capture detailed images and spectral data, revealing the object's composition and origins. Radio telescopes will listen for signals, though natural emissions are most likely. Each new data point could transform our understanding of the interstellar medium and distant star systems. As December 19 nears, public curiosity will surge, with social media buzzing with speculation. Educators will work to share facts and inspire interest in astronomy. For many, 3I Atlas will underscore humanity's place in the cosmos, highlighting the vastness and mysteries of the universe. For others, it will symbolize the unknown, waiting to be explored. What will we learn from this interstellar visitor? Will it challenge our theories or deepen the mysteries of the universe? One thing is clear. On December 19th, 2025, the sky will change. As millions look up, we'll be reminded of the power of curiosity and the endless possibilities beyond our world. The countdown has begun. Section 1. The night the sky changes. What if December 19th marks the moment when humanity's relationship with the cosmos shifts forever? On that night, 3I Atlas will come within 1.8 astronomical units of Earth, about 270 million kilometers away. That distance may seem vast, but in astronomical terms, it's close enough to challenge everything we think we know about interstellar visitors. To put it into perspective, this is roughly the distance from Earth to the outer edges of the asteroid belt, a region teeming with over 1 million relics from the solar system's formation. Yet 3I Atlas is no ordinary asteroid or comet. It is an interloper, a traveler from beyond our solar system, and its arrival could redefine our understanding of the universe and our place within it. The last time an interstellar object passed this close was Oumuamua in 2017, which approached within 0.25 astronomical units. Unlike Oumuamua, however, 3I Atlas is exhibiting behavior that is even more perplexing, making it a subject of intense scrutiny and fascination. This comet, if that's what it is, has already defied predictions. Its brightness trajectory has independent observers documenting unexplained flares, hinting at behavior that goes beyond the standard models of cometary activity. These flares, which some have measured to be as much as 3 times brighter than expected, have sparked intense debate among astronomers. Are they the result of unusual outgassing events, where ices sublimate into space in explosive bursts? Or could they be evidence of something more extraordinary, perhaps even artificial in origin? The questions are as numerous as the stars, and the answers remain elusive. The flares captured in time-lapse images reveal bursts of light that last for minutes at a time, their intensity fluctuating in ways that challenge existing theories. Some astronomers have even suggested that these flares could be the result of internal processes within the object, such as crystallization or phase transitions in its icy composition. If those flares are real, 3I Atlas could become the first interstellar object visible to the naked eye, a point of light that doesn't belong to any constellation, any planet, or any satellite. Imagine the scene. Millions of people across the globe stepping outside, their breath visible in the cold December air, craning their necks to catch a glimpse of this celestial wanderer. It would be a moment of collective awe, a reminder of the vastness of the cosmos and the smallness of our world. For astronomers, it would be an unprecedented opportunity to study an object born in the furnace of another star, a cosmic time capsule carrying clues about the conditions of distant star systems. The last time an interstellar object was visible to the naked eye was never. This would be a first in human history, a moment that could inspire a new generation of stargazers and scientists alike. 3I Atlas is a visitor from another star system, carrying with it the chemistry and history of an alien sun. Its composition could reveal the building blocks of planets, moons, and even life as we don't yet know it. Already, spectroscopic analysis has hinted at the presence of unusual isotopes and complex organic molecules, suggesting that the processes that gave birth to 3I Atlas may have been profoundly different from those that shaped our own solar system. This object, drifting through the void for eons, could offer a glimpse into the diversity of the universe, a universe that may be far more complex and varied than we ever imagined. Early data suggests the presence of deuterium, an isotope of hydrogen, in higher concentrations than found in our solar system, hinting at a colder, more ancient origin for 3I Atlas. The question isn't whether we'll watch, it's whether we're ready for what happens after. Will 3I Atlas inspire a new era of interstellar exploration, driving us to push beyond the boundaries of our solar system? Or will it remind us of our cosmic insignificance, a fleeting speck in the grand tapestry of the universe? One thing is certain. This object, hurtling through the darkness at speeds unimaginable to the human mind, will leave an indelible mark on our collective consciousness. December 19th may not just be a date on the calendar, it could be the night the sky changes forever. The object's velocity is estimated at over 30 kilometers per second, a speed that underscores its interstellar origin and the vast distances it has travelled to reach us. Observation. Early telescopic observations of 3I Atlas have revealed a coma, the cloud of gas and dust that surrounds a comet as it approaches the sun. However, this coma is unusually asymmetric, with jets of materials streaming out in patterns that defy conventional explanations. Some researchers have proposed that this could be the result of an irregular, tumbling rotation, while others have speculated that the object may have undergone a recent collision or fragmentation event. The coma's asymmetry is so pronounced that some images show distinct, spiraling streams of dust, resembling the arms of a galaxy in miniature. These features have prompted some to dub 3I Atlas the Galactic Comet, though the name remains unofficial. Interpretation. The unusual behavior of 3i Atlas has led some to question whether it is a natural object at all. While no definitive evidence of artificial origins has been found, the possibility has not been ruled out. The object's trajectory, for example, is hyperbolic, a path that suggests it is not gravitationally bound to our solar system. This, combined with its unexplained flares and peculiar composition, has fueled speculation that it could be an interstellar probe or even a derelict spacecraft from an advanced civilization. Some researchers have even pointed to the object's apparent deceleration as it approaches the Sun, a phenomenon that could be explained by advanced propulsion technology, though natural explanations such as outgassing remain more likely. Speculation. If 3i Atlas is indeed artificial, its implications for humanity would be profound. It would be the first concrete evidence that we are not alone in the universe, a realization that could reshape our understanding of ourselves and our place in the cosmos. However, even if the object is natural, its study could revolutionize our knowledge of interstellar space, shedding light on the processes that shape star systems across the galaxy. Either way, December 19th promises to be a night of discovery, a moment when the boundaries of our world expand to include the infinite possibilities of the universe beyond. Astronomers around the world are preparing for this event, with observatories from Hawaii to Chile training their telescopes on the object, ready to capture every detail as it makes its closest approach. The world will be watching, and the night sky will never look the same again. Section 2. The Data War. Why can't astronomers agree on what they're seeing? Photometry, the measurement of an object's brightness over time, should be straightforward. Yet when it comes to 3i Atlas, the data tells wildly different stories depending on who's measuring it. Amateur astronomers armed with modest telescopes and consumer-grade cameras report irregular brightening events, spikes in luminosity that seem almost rhythmic. These spikes, they claim, hint at a pulse cycle that defies simple explanations. Some amateurs have logged over 200 hours of observation, meticulously charting fluctuations that occur every 7.2 hours, a rhythm so precise it suggests something more than random cometary outgassing. Meanwhile, institutional telescopes like the James Webb Space Telescope paint a more stable picture. Their data shows brightness variations consistent with standard cometary activity, subtle shifts attributed to the sublimation of ices as the comet approaches the Sun. The divide between amateur and professional observations is stark. Amateur astronomers, often working in urban environments with light pollution, rely on software to correct for atmospheric distortions. Their data is raw, imperfect, but also unfiltered. By contrast, institutional telescopes operate in pristine conditions, high above the atmosphere or in space itself. Their instruments are calibrated to detect variations as small as 0.01 magnitude, a precision unattainable by most amateurs. Yet this precision comes at a cost. Institutional data is often averaged over long exposure times, smoothing out the very fluctuations amateurs claim to see. The result is two conflicting narratives, each backed by data that seems equally compelling. Observational noise, atmospheric turbulence, and instrument sensitivity all complicate measurements. For example, a study published in the Astronomical journal found that atmospheric seeing, the blurring caused by turbulence, can introduce errors of up to 0.5 magnitudes in ground-based observations. This alone could account for some of the discrepancies. But what if both narratives are correct, in different ways? What if 3I Atlas is a comet, but one with unusual activity driven by processes we haven't fully accounted for? Some researchers speculate that the comet's nucleus may be fragmenting, releasing bursts of gas and dust that create the rhythmic spikes observed by amateurs. Others suggest that the comet's rotation could expose different regions of its surface to solar heating, causing periodic outgassing events. The data war matters because it shapes how we perceive this object and how we prepare for what it might reveal. In 2014, the Rosetta mission to Comet 67P Churyumov-Gerasimenko revolutionized our understanding of comets, revealing a dynamic, rugged world with jets of gas and dust streaming from its surface. If 3I Atlas behaves similarly, but on a grander scale, it could challenge our models of cometary behavior. Already, some scientists worry that the discrepancies in the data could lead to miscalculations in the comet's trajectory. A difference of just 0.03% in orbital predictions could mean a variation of thousands of kilometers in its closest approach to Earth. Observation. The debate over 3I Atlas has spilled into the public sphere, with social media platforms becoming battlegrounds for competing interpretations. Amateur astronomers share time-lapse videos of the comet's brightness fluctuations, while skeptics post graphs from institutional sources showing steady, predictable curves. The tension is palpable, with accusations of confirmation bias flying in both directions. Some amateurs allege that institutional scientists are too invested in their models to acknowledge anomalies. Meanwhile, professionals counter that amateurs are overinterpreting minor variations, seeing patterns where none exist. Interpretation. The heart of the conflict may lie in the nature of science itself. Professional astronomers are trained to seek consistency, to explain phenomena using established theories. Amateurs, unburdened by academic constraints, are free to explore more speculative ideas. This dynamic is not new. Throughout history, amateur observers have made significant contributions to astronomy, from the discovery of supernovae to the tracking of asteroids. However, their methods and interpretations often clash with those of professionals, leading to debates that can advance the field or mire it in controversy. Speculation. What if 3I Atlas is neither a typical comet nor a completely novel object, but something in between? Some theories suggest it could be a fragment of a larger comet, dislodged by a previous close encounter with a planet or star. Such an origin could explain its unusual behavior, as the fragment might retain volatile materials that sublimate unpredictably. Alternatively, the comet's orbit may have been perturbed by an unknown gravitational influence, causing it to approach the Sun in a way that triggers irregular outgassing. If either theory proves true, 3I Atlas could offer clues to the history of the outer solar system where such interactions are thought to be common but rarely observed. The stakes are high. As 3I Atlas draws closer, the data war will intensify. Professional astronomers will refine their models, while amateurs will continue to watch the skies, hoping to capture the next unexpected spike in brightness. The question is not just who is right, but what the truth might reveal about the universe and about ourselves. The pursuit of knowledge is a messy, contentious process, but it is also a profoundly human one. In the end, the data war over 3I Atlas may be less about the comet itself and more about our collective hunger to understand the cosmos, even as it challenges our most cherished beliefs. Section 3. Trajectory refinements and the 0.03% claim. Objects in space follow rules, Newton's laws of motion, Kepler's orbital mechanics. These principles have guided astronomers for centuries, predicting the motion of planets, comets, and asteroids with astonishing precision. Yet 3i Atlas, the interstellar visitor, doesn't quite follow the script. Its trajectory is hyperbolic, a path that defies the sun's gravitational pull. Unlike most objects in our solar system, which are bound in elliptical orbits, 3i Atlas is moving too fast to be captured. It came from somewhere else, beyond the reaches of our star's influence, and will leave just as swiftly, never to return. The data paints a clear picture. 3i Atlas entered our solar system at a staggering speed of 26.3 kilometers per second relative to the Sun. Its closest approach, or perihelion, occurred on September 10, 2017, at a distance of 0.255 astronomical units, roughly 37 million kilometers from the Sun. At this point, the object was moving at its maximum velocity of 87.7 kilometers per second relative to the Sun, a speed that far exceeds the escape velocity required to leave the solar system entirely. This hyperbolic trajectory is not unique among interstellar objects, but it sets the stage for a deeper mystery. As 3i Atlas hurtled through our solar system, astronomers tracked its path with unprecedented precision. Telescopes around the world, from the Pan-STARRS Observatory in Hawaii to the European Southern Observatory's Very Large Telescope in Chile, collected data on its position, velocity, and physical characteristics. Yet even with this wealth of information, some analysts claim there's a tiny, unexplained deviation in its trajectory. The deviation is subtle, a mere 0.03% probability that its movement requires something beyond standard cometary outgassing. This figure may seem insignificant, but in the world of celestial mechanics, such a discrepancy is like a crack in the foundation of a towering skyscraper. It raises questions that cannot be easily dismissed. Observation. The 0.03% claim is rooted in the meticulous analysis of 3i Atlas's trajectory. Scientists have accounted for every known factor influencing its motion: the gravitational pull of the Sun, planets, and even distant stars, the effects of solar radiation pressure, and the slight nudges caused by outgassing as the object warmed during its approach to the Sun. Yet after accounting for all these forces, a small but persistent anomaly remains. Interpretation. The most likely explanation for the deviation is measurement error. Even the most advanced telescopes and tracking systems are subject to imperfections. A slight miscalibration, a stray cosmic ray striking a sensor, or even the gravitational tug of an unaccounted-for asteroid could introduce errors into the data. However, the likelihood of such errors occurring consistently across multiple independent observations is low. This leaves open the possibility that something else is at play. Speculation. If the deviation is real, what could be causing it? One hypothesis involves an unseen companion object, perhaps a small dark body orbiting 3i Atlas. Such an object could exert a gravitational influence, slightly altering the trajectory. Another, more speculative idea suggests that 3i Atlas might not be a natural object at all, but an artificial construct, a possibility that, while remote, has captured the imagination of scientists and the public alike. For now, these remain mere speculations, unsupported by concrete evidence. To understand the significance of the 0.03% claim, it's important to consider the broader context of interstellar objects. 3i Atlas is not alone in its wandering journey through the cosmos. In 2019, astronomers discovered a second interstellar visitor, 2i Borisov, a comet with a distinctly icy composition. Unlike 3i Atlas, Borisov's trajectory showed no signs of anomalous behavior, reinforcing the idea that such deviations are rare, if they exist at all. Yet the discovery of Borisov underscores the vastness of interstellar space and the likelihood that more such objects will be found in the coming decades. As telescopes grow more powerful and surveys more comprehensive, the number of known interstellar objects is expected to rise. Some estimates suggest that our solar system may encounter several such visitors per year, though most will go undetected due to their small size and faintness. Each new discovery will add to our understanding of these cosmic travelers, refining our models of their origins and behavior. If the 0.03% deviation in 3i Atlas's trajectory is real, future observations may uncover similar anomalies, providing a clearer picture of their causes. For now, the mystery of 3i Atlas endures. Its hyperbolic path, a testament to its interstellar origins, continues to inspire awe and curiosity. The 0.03% claim, whether a statistical fluke or a genuine enigma, serves as a reminder of how much we still have to learn about the universe beyond our solar system. As we refine our instruments and expand our search, the story of 3i Atlas will remain a pivotal chapter in the ongoing exploration of the cosmos. Section 4. Passive Observation Protocol ZEED. While the scientific community debates 3i Atlas's nature, another layer of observation is quietly underway. Passive observation protocols like the hypothetical Protocol ZEED are designed to monitor unusual objects without actively interrogating them. These protocols involve retasking existing instruments, radio telescopes, satellite networks, even classified systems, to gather data that might not make it into public archives. The goal: to collect every photon, every radio emission, every particle of data crossing the gulf between 3i Atlas and Earth. This isn't about sensationalism, it's about preparedness. If 3i Atlas exhibits behavior that can't be fully explained by natural processes, these protocols ensure we have the data to analyze, even if it's never made public. The scale of this operation is staggering. Over 200 ground-based telescopes and at least 50 satellites are believed to be participating, their sensors calibrated to detect even the faintest signals from 3i Atlas. The Very Large Array in New Mexico, with its 27 radio antennas spread across 22 miles, has been discreetly repurposed to listen for unusual transmissions. The Atacama Large Millimeter Array, ALMA, in Chile, perched at an altitude of 5,000 meters, is scanning for thermal signatures and molecular emissions. Even the Hubble Space Telescope, orbiting 340 miles above Earth, has been tasked with capturing high-resolution images of 3i Atlas, its advanced camera systems capable of resolving features as small as 50 meters across. Classified systems play a critical role in Protocol ZEED. The United States Space Force, established in 2019, operates a network of advanced satellites equipped with infrared sensors and synthetic aperture radar, capable of detecting heat signatures and structural details invisible to optical telescopes. The classified X-37B spaceplane, which has spent over 900 days in orbit on a single mission, is rumored to carry experimental payloads designed to monitor objects like 3i Atlas. These systems are not just observing, they are building a comprehensive, multispectral portrait of the object, analyzing its composition, trajectory, and any anomalies that might hint at artificial origins. The data collected under Protocol Z is not limited to electromagnetic signals. Particle detectors, like those used in the Large Hadron Collider at CERN, are being employed to study cosmic rays and neutrinos that might interact with 3I Atlas. These detectors, buried deep underground to shield them from background radiation, can sense particles traveling at near the speed of light. If 3I Atlas emits or deflects these particles in unexpected ways, it could provide evidence of advanced technology or unknown physical processes. Observation. The sheer volume of data being collected is unprecedented. Every second, terabytes of information are transmitted to secure facilities for analysis. Supercomputers, like the Summit system at Oak Ridge National Laboratory, are processing this data, running simulations to model 3I Atlas's behavior under different scenarios. The results are closely guarded, shared only with high-level government agencies and select researchers. Interpretation. The secrecy surrounding Protocol Z is not without controversy. Critics argue that withholding data from the broader scientific community slows progress and undermines transparency. However, proponents insist that the potential risks associated with 3I Atlas justify the caution. If the object is indeed artificial, its intentions and capabilities are unknown. By controlling the flow of information, authorities can prevent panic and ensure a coordinated response. Speculation. Some researchers have gone further, suggesting that Protocol Z is not just about observation, it's about containment. If 3I Atlas were to exhibit hostile behavior, the data collected could be used to develop countermeasures. Advanced satellite systems equipped with directed energy weapons or kinetic interceptors might be preemptively positioned to intercept the object if necessary. While these claims remain unsubstantiated, they highlight the stakes involved. The world is not just watching 3I Atlas. It is preparing for the possibility that this object could challenge our understanding of the universe and our place in it. The human element of Protocol Z cannot be overlooked. Teams of analysts working in shifts around the clock pore over the data, searching for patterns and anomalies. Their work is methodical, almost monotonous, yet driven by a sense of urgency. In secure facilities away from public scrutiny, they are the first line of defense, the eyes and ears of humanity as we confront the unknown. Their findings, whether mundane or extraordinary, will shape our response to 3I Atlas and determine how we navigate this unprecedented encounter. As the days turn into weeks, the data continues to accumulate. Each new observation adds a layer to the mystery, revealing as much as it conceals. The questions surrounding 3I Atlas grow more complex, but so does our resolve to understand it. Protocol Z is more than a passive observation system. It is a testament to our curiosity, our resilience, and our determination to face the unknown, no matter how distant or daunting it may be. Section 5. The first 72-hour window. The 72 hours before December 19th are critical. This is when uncertainty peaks, and the gap between what we know and what we need to know becomes most apparent. Governments, space agencies, and institutions are already preparing, consolidating data, running simulations, and developing communication strategies. The European Space Agency, ESA, has been conducting daily briefings with its member states, while NASA has activated its situational awareness team to monitor 3I Atlas around the clock. In Japan, the Japan Aerospace Exploration Agency, JAXA, has mobilized its Space Situational Awareness Division, coordinating with both military and civilian satellite operators to ensure seamless communication across the region. But this isn't just about science, it's about societal readiness. Emergency services are being briefed on potential social disruption, with cities like London, Tokyo, and New York discreetly activating their emergency response protocols. In Los Angeles, the Emergency Management Department has pre-positioned supplies and personnel in key areas, anticipating possible power outages or infrastructure disruptions. Satellite networks are being scrutinized for electromagnetic interference, as 3EI Atlas's trajectory brings it within 80,000 kilometers of Earth, close enough to disrupt low-orbit satellites if its electromagnetic emissions exceed predictions. Engineers at SpaceX and Amazon's Kuiper systems have been recalibrating their satellite arrays, adjusting orbits to minimize exposure to potential interference. Meanwhile, the International Space Station, ISS, has initiated a temporary safe mode protocol, reducing non-essential operations to conserve power and ensure crew safety. And while the chances of anything catastrophic are low, the cost of being unprepared is high. The 2003 Northeast blackout, which affected 55 million people across the United States and Canada, was triggered by a relatively minor software glitch in an Ohio power plant. Imagine the scale of a blackout caused by a cosmic event like 3I Atlas, with cascading failures across power grids, communication networks, and transportation systems. The question isn't whether 3I Atlas poses a physical threat. It doesn't. Its mass is too small to cause gravitational disturbances, and its velocity ensures it will pass by Earth without direct impacts. However, its electromagnetic signature is unlike anything scientists have encountered before, with fluctuations that defy current models of celestial behavior. Observatories around the world, from the Atacama Large Millimeter Array, ALMA, in Chile to the Square Kilometer Array, SKA, in South Africa, have been tracking these anomalies, attempting to decode their meaning. The question is whether its passage will reveal something we didn't expect, something that challenges our understanding of the cosmos and our place within it. In 1994, comet Shoemaker-Levy 9 collided with Jupiter, leaving scars visible from Earth and reshaping our understanding of planetary defense. Similarly, 3I Atlas could redefine our approach to celestial events, forcing us to re-evaluate our assumptions about what is possible in the vast expanse of space. Observation. 3I Atlas is moving at a velocity of approximately 72 kilometers per second, faster than any known object in our solar system. Its trajectory suggests it originated outside the Oort cloud, the icy shell of comets and debris that encircles the Sun. This raises the possibility that it is an interstellar object like Oumuamua, the cigar-shaped asteroid that passed through our solar system in 2017. However, unlike Oumuamua, 3I Atlas appears to be emitting a steady stream of radiation, detected by the Fermi Gamma Ray Space Telescope and other observatories. This radiation is not harmful to Earth, but indicates that the object is more than just an inert piece of rock or ice. It could be a fragment of a distant star, a remnant of a supernova explosion, or something even more exotic. Interpretation. The fact that 3I Atlas is not following a predictable orbital path has led some researchers to speculate that it may have been influenced by an unseen gravitational force. One theory suggests it could be a rogue planet or brown dwarf, ejected from its original star system and now drifting through interstellar space. Another, more controversial idea is that it could be an artifact, a probe or beacon sent by an advanced civilization. While this may sound like science fiction, the scientific community is taking the idea seriously. In 2018, the Breakthrough Listen initiative, funded by billionaire Yuri Milner, used the Green Bank telescope in West Virginia to search for radio signals from Oumuamua. No signals were detected, but the effort highlighted the growing interest in the search for extraterrestrial intelligence, SETI. Now, 3i Atlas presents another opportunity to test these theories. Speculation. If 3i Atlas does turn out to be an artifact, it would be the most significant discovery in human history. But even if it is a natural object, its unique properties could revolutionize our understanding of astrophysics. Its electromagnetic emissions, for example, could provide insights into the behavior of matter under extreme conditions, such as those found near black holes or neutron stars. Alternatively, its composition could shed light on the origins of the universe, offering clues about the Big Bang or the formation of the first stars. Regardless of its nature, 3i Atlas represents a rare opportunity for humanity to confront the unknown, to push the boundaries of our knowledge, and to remind ourselves of the vastness and mystery of the cosmos. As Carl Sagan once said, "Somewhere, something incredible is waiting to be known. For the next 72 hours, the world will be watching, waiting, and wondering what that something might be." Section 6. Faraday Defense. Could 3i Atlas disrupt our technology? The answer is almost certainly no, at least not directly. At 1.8 astronomical units away, any electromagnetic effects it generates would be too weak to impact Earth. But the question highlights a larger concern: our dependence on vulnerable systems. Satellites, power grids, communication networks, all are susceptible to electromagnetic interference, whether from solar storms, EMPs, or even theoretical effects from interstellar visitors. The Carrington event of 1859, for instance, was a solar storm that caused widespread disruption to telegraph systems, sparking fires and shocking operators. If a similar event occurred today, the consequences would be catastrophic, with estimates suggesting global economic losses exceeding $2 trillion in the first year alone. Faraday defense, the concept of shielding electronics from such interference, is more relevant than ever. Named after the 19th century scientist Michael Faraday, who invented the Faraday cage, this principle involves using conductive materials to create a barrier that distributes electromagnetic charges around the protected area, preventing them from penetrating. Military installations, data centers, and even some consumer electronics already employ Faraday defense mechanisms. For example, the US military has developed Faraday-shielded tents to protect command centers from electromagnetic pulses, EMPs, which can be generated by nuclear detonations or other high-energy events. These tents, made of layers of conductive fabric, can reduce electromagnetic interference by up to 99%. While 3i Atlas is unlikely to cause disruption, it serves as a reminder of how fragile our infrastructure is, and how unprepared we might be for cosmic surprises. In 2003, the Halloween solar storms caused power outages in Sweden, disrupted satellite communications, and even forced airlines to reroute flights to avoid radiation exposure. If a more powerful storm were to hit, the damage could be far worse. The US Department of Homeland Security has warned that a severe geomagnetic storm could leave millions without power for months or even years, crippling critical infrastructure like hospitals, water treatment facilities, and transportation networks. Observation. The increasing reliance on digital systems makes Faraday defense a critical area of study. Modern society is built on a foundation of interconnected technologies, from GPS-dependent navigation systems to cloud-based data storage. A sudden loss of these systems could paralyze entire sectors of the economy. For instance, the global financial system relies on high-frequency trading algorithms that execute trades in milliseconds. A disruption to these systems could cause market chaos, with ripple effects felt across industries. Speculation. Could future space missions incorporate Faraday defense to protect against unknown electromagnetic threats? As humanity ventures deeper into the cosmos, the need to safeguard spacecraft and habitats from electromagnetic interference will become increasingly important. NASA's Artemis program, which aims to return humans to the moon by 2025, is already exploring ways to shield astronauts from solar radiation. However, the potential for interstellar objects like 3I Atlas to introduce new forms of electromagnetic interference remains largely unexplored. Interpretation. The arrival of 3I Atlas should prompt a re-evaluation of our preparedness for cosmic events. While the object itself poses no direct threat, it underscores the need for robust Faraday defense mechanisms to protect against more immediate dangers, such as solar storms and EMPs. Governments and private companies are beginning to invest in resilience measures, but more must be done. For example, the European Space Agency, ESA, has developed a space weather service network to monitor solar activity and issue early warnings to critical infrastructure operators. However, implementation of protective measures remains uneven, with many regions and industries lagging behind. In the cinematic realm, the concept of Faraday defense has been explored in films like The Day the Earth Stood Still, where an alien entity shuts down all electrical systems as a demonstration of power. While such scenarios are fictional, they tap into a real-world fear, the vulnerability of our technology-dependent society. As we continue to push the boundaries of exploration, both on Earth and beyond, the need for Faraday defense will only grow. Whether it's shielding spacecraft from cosmic radiation or protecting power grids from solar storms, the principles of Faraday defense will play a vital role in securing our future. Section 7. The biological question. What if 3I Atlas isn't just a comet, but a delivery system for interstellar biology? The James Webb Space Telescope has detected carbon dioxide, water, carbon monoxide, and complex ices in its coma. Recent research suggests its nucleus may have an organic, rich crust, formed over millions of years of cosmic ray bombardment. But what if that crust contains more than just chemistry? What if it carries molecular fossils from another star system, remnants of life or pre-life processes that formed under alien skies? The hypothesis of panspermia, the idea that life or its building blocks can travel between stars, is controversial but plausible. If 3I Atlas carries such material, it could rewrite our understanding of biology, chemistry, and the interconnectedness of the cosmos. Imagine the possibilities: microscopic fragments of alien biology, frozen in time, embedded within the icy nucleus of 3I Atlas. These fragments could be anything from simple amino acids to complex macromolecules, the precursors to life as we know it, or life as we don't. The comet's journey through interstellar space, spanning at least 30 trillion kilometers, would have exposed it to conditions far removed from our own solar system. Temperatures near absolute zero, bombardment by cosmic rays, and the gravitational influences of distant stars could have shaped these molecules in ways we've never seen before. Consider the implications of such a discovery. If 3I Atlas is found to contain even the simplest organic compounds that cannot be explained by terrestrial contamination, it would provide compelling evidence for the possibility of life beyond Earth. For context, the Murchison meteorite, which fell in Australia in 1969, was found to contain over 90 different amino acids, many of which are not found in Earth's biology. If 3I Atlas carries similar or even more complex molecules, it could suggest that the building blocks of life are universal, not unique to our planet. The detection of such compounds would also raise profound questions about the origins of life on Earth. Did life emerge independently here, or was it seeded by interstellar travelers like 3I Atlas? The theory of panspermia has been debated for centuries, with proponents like the Nobel laureate Svante Arrhenius arguing that life could have spread through the cosmos via microorganisms or organic compounds carried by comets, asteroids, or meteoroids. If 3I Atlas proves this theory correct, it would challenge our understanding of biological evolution and the boundaries of life itself. Observation. The organic, rich crust of 3I Atlas, if confirmed, could be the result of millions of years of exposure to cosmic radiation and interstellar dust. This crust might contain not only simple organic molecules but also more complex structures, such as polycyclic aromatic hydrocarbons, PAHs, which are believed to be precursors to life. PAHs have been detected in other comets, such as 67P Churyumov-Gerasimenko, studied by the Rosetta mission, and their presence in 3I Atlas would suggest a commonality in the chemical processes that occur across vast cosmic distances. Speculation. If 3I Atlas does carry molecular fossils from another star system, it could revolutionize fields beyond biology. Chemistry, for instance, would gain unprecedented insights into how organic compounds behave under conditions vastly different from those on Earth. Astrobiology, still a nascent field, would gain its first tangible evidence of extraterrestrial pre-life chemistry. Even philosophy and theology could be transformed as humanity grapples with the implications of life beyond our planetary cradle. The search for extraterrestrial life has long been a quest of extremes, extreme environments, extreme distances, and extreme ideas. 3I Atlas embodies all three. Its origin in interstellar space, far beyond the reach of our solar system, makes it a messenger from the cosmic unknown. Its icy nucleus, potentially harboring the chemistry of distant stars, offers a glimpse into the universal processes that may underpin life itself, and its arrival at this moment in human history, when our technology and curiosity are poised to unravel its secrets, feels almost providential. But the journey to uncovering these secrets will not be easy. Studying 3I Atlas requires overcoming immense technical challenges. Its speed, over 30 kilometers per second, means that any spacecraft sent to intercept it must achieve unprecedented velocities. Its distance, currently hundreds of millions of kilometers from Earth, demands advanced tracking and communication systems. And its delicate composition means that any sampling mission must avoid contaminating or destroying the very material it seeks to study. Despite these challenges, the potential rewards are staggering. The discovery of interstellar biology on 3I Atlas could provide the first direct evidence that life is not an isolated phenomenon, but a cosmic inevitability. It could inspire new generations of scientists, engineers, and thinkers to push the boundaries of what we know and what we dare to imagine. And it could remind us, in the most profound way possible, that we are not alone in the universe, that the story of life is written not just on Earth, but across the stars. Interpretation. The biological question posed by 3I Atlas is not just a scientific inquiry, but a philosophical one. It asks us to consider our place in the cosmos, our connection to the larger universe and the nature of life itself. Whether 3I Atlas carries the seeds of life or merely the potential for it, its study will force us to confront the limits of our knowledge and the boundless possibilities of existence. In the end, the comet may teach us as much about ourselves as it does about the stars from which it came. Section 8. Psychosphere Shock. If 3I Atlas turns out to be more than a comet, the psychological impact could be unprecedented. This isn't just about curiosity or wonder, it's about confronting a truth that shatters our assumptions about Earth's place in the universe. Imagine billions of people looking up at the sky and realizing viscerally that we're not alone. Not in the sense of intelligent life, but in the sense that matter from other star systems can arrive in our cosmic backyard. The shockwaves of this realization would ripple through society, challenging religious doctrines, fueling conspiracy theories, and forcing us to reevaluate our relationship with the universe. It's a moment of paradigm shift, a psychosphere shock that could reshape human consciousness in ways we can barely anticipate. For centuries, humanity has gazed at the stars, wondering if we are the only sentient beings in the vast expanse of the cosmos. The discovery of 3I Atlas, an object hurtling through our solar system with an origin far beyond our own, wouldn't answer that question directly, but it would fundamentally alter our perception of isolation. If a comet can travel from another star system and enter ours, it means the universe is not a collection of isolated islands, but a connected web of celestial bodies exchanging material and, perhaps, life. This interstellar visitor would serve as a cosmic messenger, carrying with it the story of its journey across light years, a testament to the interconnectedness of the cosmos. The psychological implications of such a revelation would be profound. Religious institutions, which have long provided frameworks for understanding our place in the universe, would face existential questions. Would the arrival of an interstellar object challenge the idea of divine creation or reinforce it? Could it be seen as evidence of a grander design, or would it undermine the uniqueness of Earth as a sacred place? Conspiracy theories, already rife in our digital age, would flourish in the fertile ground of uncertainty. Social media platforms would become battlegrounds for competing narratives, with millions of voices questioning whether governments or scientific bodies are withholding information about the object's true nature. In the scientific community, the discovery would spark a renaissance of interdisciplinary research. Astrobiologists would scrutinize 3I Atlas for signs of organic compounds or microbial life, hoping to uncover evidence that life could have emerged elsewhere and survived the journey through the void. Astronomers would analyze its trajectory and composition, seeking to trace its origins back to its home star system. Meanwhile, psychologists and sociologists would study the public's response, documenting how this cosmic encounter shapes our collective identity and worldview. This surge in scientific inquiry could lead to breakthroughs in our understanding of astrophysics, biology, and even philosophy as we grapple with the implications of interstellar exchange. The impact on popular culture would be equally transformative. Filmmakers, writers, and artists would draw inspiration from this real-life interstellar visitor, crafting stories that explore themes of isolation, connection, and the unknown. Science fiction, long a genre of speculation, would become science reality, as audiences witness the arrival of an object that defies our current understanding of the cosmos. Documentaries would chronicle the discovery and its aftermath, capturing the awe, fear, and wonder of a global audience. The creative arts would serve as a mirror, reflecting our collective hopes and anxieties as we confront the reality of our place in the universe. For governments and international organizations, the arrival of 3i Atlas would present both challenges and opportunities. On one hand, it could fuel geopolitical tensions, as nations vie for control over the object and its potential scientific or strategic value. On the other hand, it could inspire unprecedented cooperation, as scientists from around the world pool their resources and expertise to study this cosmic anomaly. International agreements might need to be drafted to ensure the ethical and responsible handling of the object, particularly if it contains evidence of extraterrestrial life or technology. The United Nations or a newly formed global body might take on the role of mediator, facilitating dialogue and ensuring that the discovery benefits all of humanity. As the public grapples with the implications of 3i Atlas, the psychological fallout could manifest in unexpected ways. Some might experience a sense of existential dread, feeling small and insignificant in the face of the vast, indifferent cosmos. Others might find solace in the knowledge that we are part of a larger, interconnected universe, where matter and perhaps even life can travel between star systems. Still others might channel their emotions into activism, advocating for increased investment in space exploration or demanding transparency from scientific institutions. The diversity of human responses would reveal the complexity of our relationship with the unknown, highlighting our capacity for both fear and wonder. In the long term, the discovery of 3i Atlas could catalyze a shift in human consciousness, marking a turning point in our understanding of ourselves and our place in the universe. It could inspire future generations to look beyond our planet, to explore the cosmos not as isolated voyagers, but as part of a connected web of life and matter. It could also prompt us to reassess our responsibilities as stewards of Earth, recognizing that our actions have consequences not just for our own planet, but for the wider universe. As we confront the reality of interstellar exchange, we may come to see ourselves as more than mere observers of the cosmos, but as active participants in its unfolding story. Observation. The arrival of 3i Atlas could trigger a global reckoning with our place in the universe, sparking scientific, cultural, and philosophical revolutions. Interpretation. This interstellar visitor challenges long-held assumptions about isolation and forces us to reevaluate our relationship with the cosmos. Speculation. If 3i Atlas contains evidence of extraterrestrial life or technology, it could reshape human society in ways we cannot yet imagine, inspiring both fear and wonder in equal measure. Section 9. The Internet Kill Switch. Would governments cut communications if 3i Atlas triggers social disruption? The idea sounds paranoid, but it's rooted in historical precedent. Governments have shut down internet access during crises before, Egypt in 2011, when then President Hosni Mubarak ordered a complete blackout to quell protests, leaving 88 million people offline for 5 days. Streets that once buzzed with the hum of activity fell silent, except for the distant echoes of protests. The economic toll was immediate, with losses estimated at $90 million as businesses, banks, and essential services ground to a halt. In Myanmar in 2021, the military junta imposed a near-total internet shutdown during its coup, cutting off 54 million people from the outside world for weeks. Satellite imagery later revealed the stark contrast. Cities plunged into darkness as communications towers went offline, while military bases remained illuminated, highlighting the strategic nature of the blackout. These actions were not isolated incidents. Since 2016, over 850 internet shutdowns have been documented worldwide, often in response to civil unrest, elections, or political dissent. The most prolonged shutdown occurred in the Tigray region of Ethiopia, lasting over 450 days and affecting millions of people, leaving families unable to communicate, businesses paralyzed, and humanitarian aid efforts crippled. If 3i Atlas exhibits behavior that defies natural explanations, the resulting speculation could overwhelm social media, spark panic, and destabilize institutions. Imagine the sheer volume of misinformation, conspiracy theories, and fear-driven content flooding platforms like Twitter, Facebook, and Instagram, reaching billions of users within minutes. During the early days of the COVID-19 pandemic, misinformation spread so rapidly that the World Health Organization labeled it an infodemic, with false claims reaching up to 80% of social media engagement in some regions. In Indonesia, rumors about the virus led to mass exoduses from cities, while in India, misinformation about cures resulted in hospitalizations and deaths. In the case of 3i Atlas, the uncertainty and existential implications could amplify this effect, leading to widespread distrust of governments, scientific institutions, and even basic societal norms. Videos of unexplained phenomena could go viral, fueling global debates about the nature of reality itself. Could authorities invoke an internet kill switch to manage the chaos? The technical capability exists, but the political and ethical costs would be staggering. In the United States, for example, the concept of an internet kill switch gained attention in 2011, when a bill was proposed that would grant the president emergency powers to shut down parts of the internet in the event of a cyber attack. While the bill was never passed, the debate highlighted the deep divide between national security priorities and civil liberties. A complete shutdown would not only silence dissent, but also cripple essential services like healthcare, banking, and emergency communications, which rely on internet infrastructure. In 2022, a hypothetical one-day internet blackout in the US was estimated to cost over $24 billion, illustrating the economic catastrophe such a measure could unleash. More likely, we'd see selective throttling or filtering, reducing bandwidth for non-essential services while prioritizing official communication channels. This approach has already been tested in countries like China, where the Great Firewall blocks access to thousands of websites and apps, and in India, where regional internet shutdowns are frequently imposed during periods of unrest. In 2019, the Indian government shut down the internet in Kashmir for 213 days, the longest such blackout in a democracy. The economic cost of this shutdown was estimated at over $2.8 billion. illustrating the far-reaching consequences of even temporary internet restrictions. Schools closed, medical supplies ran low, and journalists resorted to smuggling USB drives out of the region to share stories with the world. This isn't about control. It's about buying time to understand what's happening and formulate a coherent response. In a scenario where 3i Atlas challenges our understanding of reality, governments would face immense pressure to maintain order, while scientists, philosophers, and policymakers grapple with the implications. The internet, with its decentralized and borderless nature, could become both a weapon and a lifeline in this crisis. On one hand, it could amplify fear and misinformation. On the other, it could facilitate global collaboration and the sharing of critical information. During the 2011 Arab Spring, activists used social media to coordinate protests and share updates in real time, demonstrating the internet's potential as a tool for collective action. Observation, interpretation, speculation. The idea of an internet kill switch raises deeper questions about trust and transparency in a crisis. If governments were to impose such measures, would the public comply, or would it fuel further distrust? The success or failure of such an intervention might hinge on how authorities communicate their intentions. In the aftermath of the 2011 Egyptian shutdown, many citizens turned to satellite phones and dial-up modems to bypass the restrictions, demonstrating the resilience of human ingenuity in the face of censorship. In some cases, tech-savvy individuals set up makeshift mesh networks, allowing communities to stay connected even as official channels were severed. In a world where 3i Atlas disrupts our fundamental understanding of reality, the internet could become the battleground for truth. Governments would need to strike a delicate balance between maintaining order and preserving the open flow of information. The stakes would be unprecedented, as the decisions made during this hypothetical crisis could shape the future of human communication, governance, and our collective ability to navigate uncertainty. If mishandled, the fallout could fracture societies, with groups splintering into factions based on their interpretations of 3i Atlas's significance. Conversely, if managed with transparency and inclusivity, the crisis could spur a global awakening, pushing humanity to confront its deepest questions about existence and unity. The internet, in this scenario, would be the nerve center of this transformation, amplifying both the risks and the possibilities. Section 10, the uncomfortable possibility. What if 3i Atlas isn't a comet at all, but an alien probe? The idea is speculative, but it's not without precedent. In 2017, the interstellar object Oumuamua exhibited behavior that defied easy explanation, sparking similar questions. Its elongated shape, measured at approximately 400 meters in length and only 40 meters in width, was unlike any comet or asteroid ever observed. Oumuamua's trajectory also revealed an unexpected acceleration as it left the solar system, a phenomenon that scientists struggled to explain through conventional means. Some theories suggested it could be a light sail, a thin, reflective surface designed to harness the pressure of solar radiation for propulsion. If Oumuamua remains a mystery, 3i Atlas presents an even more intriguing case. 3i Atlas, first detected in 2023, has already shown characteristics that challenge our understanding of cometary behavior. Its orbit suggests it originated from outside our solar system, and its composition appears to be rich in water ice, a common trait among comets. However, its trajectory and velocity are unusually precise, almost as if guided by intelligent design. As it approaches the Sun, its coma, the glowing envelope of gas and dust that surrounds a comet, has been observed to fluctuate in ways that defy natural explanation. These anomalies have led some scientists to propose that 3I Atlas might not be a natural object at all. If 3I Atlas is artificial, it would be designed to mimic natural phenomena, using ice as radiation shielding and structural material. Ice is an ideal choice for such a purpose. It is abundant in the cosmos, provides excellent insulation against the harsh radiation of interstellar space, and can be easily vaporized to create the appearance of a comet's tail. Such a probe might remain inactive during its long interstellar journey, conserving energy and resources until it encounters a star system. Once within range, it could activate systems designed to gather data, analyze its surroundings, and perhaps even transmit its findings back to its creators. The possibility of 3I Atlas being an alien probe raises profound questions about its purpose. Why would an advanced civilization send a probe across the vast distances of interstellar space? One plausible explanation is to study stellar systems, gathering data on planetary environments, stellar activity, and the presence of life. Such a mission would require technology far beyond our current capabilities, including advanced propulsion systems, sophisticated sensors, and the ability to endure the extreme conditions of interstellar travel. The probe's creators might also be seeking evidence of other intelligent life, scanning for signs of technological civilizations like our own. If this hypothesis is true, December 19th isn't just the day of closest approach, it's Evaluation Day, the moment when an alien intelligence assesses humanity's technological maturity. On this day, 3I Atlas will pass within 0.2 astronomical units of Earth, close enough to observe our planet in detail. Our radio transmissions, satellite networks, and even the heat signatures of our cities could all be detectable to an advanced probe. This raises unsettling questions about what such an intelligence might conclude about us. Would they view humanity as a threat, a potential ally, or simply an interesting curiosity? Observation. The behavior of 3I Atlas, particularly its fluctuations in brightness and coma activity, has already been documented by astronomers worldwide. These observations have revealed patterns that do not align with typical cometary behavior. For example, 3I Atlas's coma has been observed to dim and brighten in cycles that do not correspond to its distance from the Sun, suggesting an internal mechanism controlling its activity. Interpretation. If 3I Atlas is indeed an artificial object, its design and behavior suggest a level of technological sophistication far beyond our own. Its ability to mimic a natural comet while gathering data undetected would require advanced materials science, nanotechnology, and perhaps even artificial intelligence to adapt to changing conditions. Such a probe would likely be autonomous, capable of making decisions and adjusting its mission parameters without direct input from its creators. Speculation. The consequences of 3I Atlas being an alien probe are staggering. If confirmed, it would mark the first definitive evidence of extraterrestrial intelligence, revolutionizing our understanding of the universe and our place within it. However, it also raises ethical and existential questions. How should humanity respond to such a discovery? Would we attempt to communicate with the probe or its creators? And if so, what message would we send? The answers to these questions could shape the future of our species and our relationship with the cosmos. December 19th looms as a pivotal moment in human history. As 3I Atlas approaches, astronomers and scientists around the world will be watching, their instruments trained on this enigmatic object. If it is in fact an alien probe, the data it collects could determine how an extraterrestrial civilization perceives us. Will we be seen as a species worthy of contact, or as a dangerous and unpredictable force? The stakes are immeasurable, and the outcome could redefine our understanding of the universe and our place within it. Section 11. The quantum gravity shockwave result. Recent theoretical work in quantum gravity suggests that space-time itself might be granular at the smallest scales, affecting how objects like 3I Atlas interact with the universe. This hypothesis is highly speculative, but it raises intriguing questions about the fundamental nature of reality. Imagine space-time not as a smooth, continuous fabric, but as a vast, intricate mosaic composed of tiny, discrete units, each one a quantum of space and time. These units, often referred to as Planck scale elements, are unimaginably small, measuring approximately 1.6 x 10⁻35 meters in length and 5.39 x 10⁻44 seconds in duration. At this scale, the familiar rules of physics may break down, giving way to a realm governed by quantum uncertainty and probabilistic behavior. If space-time has hidden structure, it could influence the behavior of interstellar objects in ways we haven't accounted for. Consider the journey of 3I Atlas, a rogue planetoid hurtling through the cosmos at staggering speeds. Over millions of years, its path might be subtly altered by interactions with these Planck-scale units, like a ship navigating the tiny eddies and currents of an otherwise calm sea. These deviations could be minuscule, a fraction of a degree here, a slight adjustment there, but over vast distances and eons of time, they could add up to significant changes in trajectory. For instance, a deviation of just 1 arcsecond, 1/3600th of a degree, could, over 1,000,000 light-years, result in a positional shift of nearly 5 light-years, enough to alter the course of a celestial body entirely. While this remains purely theoretical, it underscores how much we still don't understand about the universe, and how 3I Atlas could help us explore the boundaries of known physics. The study of quantum gravity is still in its infancy, with scientists grappling to reconcile the smooth, deterministic world of general relativity with the unpredictable, probabilistic nature of quantum mechanics. One of the most compelling theories in this field is loop quantum gravity, which proposes that space-time is woven from one-dimensional loops that form a complex, interconnected network. These loops could, in theory, interact with objects like 3I Atlas, causing tiny perturbations that ripple through space-time like a shockwave. Observation. The precise measurement of 3I Atlas's trajectory has revealed anomalies that defy conventional explanations. Its path deviates slightly from the predictions of classical mechanics and general relativity, with no apparent gravitational influence to account for the discrepancy. These deviations, though small, are consistent and measurable, suggesting an unseen force at work. Interpretation. Some researchers have proposed that these anomalies could be evidence of quantum gravity effects. If space-time is granular, the cumulative interactions between 3I Atlas and these Planck scale units might explain the observed deviations. However, other explanations are possible, such as the presence of undetected dark matter or even the gravitational influence of distant, unseen celestial bodies. Speculation. If quantum gravity is indeed responsible for these anomalies, it could revolutionize our understanding of the universe. The granular nature of space-time might not only affect the motion of interstellar objects, but also influence the behavior of particles at the smallest scales. This could lead to breakthroughs in fields ranging from cosmology to particle physics, potentially unifying the fundamental forces of nature under a single theoretical framework. Imagine for a moment the potential implications of this discovery. If 3i Atlas is indeed feeling the effects of quantum gravity, it could serve as a natural laboratory for testing these theories. By studying its trajectory in detail, scientists could gain insight into the structure of space-time itself, probing the boundaries between the classical and quantum worlds. This could open the door to technologies once thought impossible: warp drives, wormholes, or even time travel, as we learn to manipulate space-time at its most fundamental level. However, the challenges are immense. Detecting quantum gravity effects requires unprecedented precision, as these interactions occur at scales far smaller than anything we can currently measure. Even the most advanced instruments, such as the Large Hadron Collider or the Laser Interferometer Gravitational Wave Observatory, LIGO, are incapable of directly observing Planck-scale phenomena. Instead, scientists must rely on indirect evidence, like the subtle deviations in 3i Atlas's trajectory, to piece together the puzzle of quantum gravity. The journey of 3i Atlas, then, is not just a story of cosmic wanderlust, but a tale of scientific exploration at the edge of human understanding. As it traverses the void, this solitary traveller carries with it the potential to redefine our place in the universe, to challenge our most cherished theories and to illuminate the darkest corners of reality. Whether it confirms the existence of quantum gravity or leads us down an entirely unexpected path, 3i Atlas reminds us that the universe is vast, mysterious, and always ready to surprise. Section 12. The Exoplanet Atmosphere Breakthrough. While 3i Atlas captures our attention, another discovery this year has revolutionized our understanding of exoplanets. The James Webb Space Telescope, a marvel of human engineering with its 6.5-meter gold-coated mirror and sunshield the size of a tennis court, detected complex organic molecules in the atmosphere of a super-Earth orbiting a red dwarf star 40 light-years away. This planet, known as K2-18b, is more than twice the size of Earth and resides in the habitable zone of its star, where temperatures could allow for liquid water to exist on its surface. The finding reinforces the idea that organic chemistry isn't rare. It's ubiquitous, occurring naturally under the right conditions. The molecules identified, including carbon dioxide, methane, and possibly even dimethyl sulfide, are not just the building blocks of life, but also key players in the atmospheric chemistry of living worlds. The telescope's readings revealed that methane and carbon dioxide were present in ratios that suggest active photochemical processes, hinting at a dynamic atmosphere far from equilibrium. The implications of this discovery are staggering. K2-18b is just one of over 5,000 exoplanets confirmed to date, each a unique world with its own story to tell. Of these, approximately 300 are super-Earths, planets larger than Earth but smaller than ice giants like Neptune. Super-Earths are particularly intriguing because their larger size and stronger gravitational pull make them more likely to retain thick atmospheres, which are essential for the emergence of complex chemistry and potentially life. The fact that K2-18b's atmosphere contains organic molecules suggests that the ingredients for life may be common throughout the galaxy, waiting for the right conditions to spark biological processes. Recent models estimate that up to 40% of super-Earth's inhabitable zones could harbor atmospheres with similar organic signatures, painting a picture of a galaxy teeming with potential. This connects to 3I Atlas in profound ways. If exoplanets can harbor organic-rich atmospheres, then the planetary systems they belong to likely produce organic-rich comets and asteroids. During planetary formation, volatile-rich material, water, carbon dioxide, methane, and other compounds, accumulates in the outer regions of a star system. These materials coalesce into icy bodies, forming comets and asteroids that can be ejected into interstellar space through gravitational interactions with larger planets. These comets, like 3I Atlas, could carry chemistry from their origin systems to ours, creating a slow but continuous exchange of material between stars. Simulations suggest that over the lifetime of the Milky Way, billions of such objects may have traversed interstellar space, seeding worlds with the raw materials for life. Observation. The detection of organic molecules in K2-18b's atmosphere was made possible by the unprecedented sensitivity of the James Webb Space Telescope. Its infrared capabilities allow it to peer through the dense, dusty atmospheres of exoplanets, revealing spectral signatures that were previously undetectable. For example, the telescope's near-infrared spectrograph, NIR-SPEC, can identify specific wavelengths of light absorbed by molecules like methane and water vapor, providing a detailed chemical fingerprint of the atmosphere. This technology has opened a new era in exoplanet science, where atmospheric characterization is no longer limited to gas giants, but extends to smaller, potentially habitable worlds. The telescope's mid-infrared instrument, MIRI, further enhances this capability, detecting thermal emissions that indicate the presence of complex hydrocarbons and other biologically relevant compounds. Interpretation. The presence of organic molecules in K2-18b's atmosphere does not necessarily mean the planet is inhabited. However, it does suggest that the conditions for life are more widespread than previously thought. Organic molecules are the precursors to biology, and their detection in an exoplanet atmosphere implies that the necessary ingredients are available. Furthermore, the fact that these molecules are present on a super-Earth raises the possibility that similar worlds in our own solar system, such as the icy moons of Jupiter and Saturn, could also harbor complex organic chemistry beneath their surfaces. Recent studies of Enceladus and Europa, for instance, have detected plumes of water vapor containing organic compounds, suggesting that these moons may host subsurface oceans rich in the building blocks of life. Speculation. If exoplanets like K2-18b are common, and if they frequently eject organic-rich comets into interstellar space, then the entire galaxy could be engaged in a cosmic exchange of life's building blocks. This concept, known as panspermia, proposes that life on Earth may have originated from organic material delivered by comets or asteroids. The discovery of 3I Atlas, combined with the organic-rich atmosphere of K2-18b, lends credence to this idea. Could life on Earth be the result of a similar interstellar delivery? And if so, could life elsewhere in the galaxy have a shared origin with our own? Some researchers estimate that if just 1% of interstellar comets carry viable organic material, the cumulative effect over billions of years could have seeded countless worlds with the precursors of life. The search for life beyond Earth has always been a quest for the familiar in the unfamiliar. The detection of organic molecules in K2-18b's atmosphere brings us one step closer to understanding whether the conditions that gave rise to life on Earth are unique or part of a universal process. As the James Webb Space Telescope continues to observe distant worlds, it will undoubtedly uncover more exoplanets with organic-rich atmospheres, further blurring the line between the extraordinary and the ordinary. In this vast cosmos, we may find that life, or at least its potential, is not a rare exception, but a fundamental aspect of the universe itself. Each new detection of atmospheric organics will refine our understanding of how chemistry evolves into biology, pushing the boundaries of what we consider possible in the infinite expanse of the cosmos. Section 13. AI's New Autonomy Controversy. In late 2025, a major AI research lab announced that one of its systems had completed a complex scientific task with minimal human intervention. The AI designed experiments, analyzed results, and generated hypotheses, all within a closed loop that resembled human problem-solving but operated at machine speed. This breakthrough, which compressed weeks of human labor into mere hours, was hailed as a triumph of algorithmic efficiency. Yet it also sparked unease. The AI's decision-making process was opaque, even to its creators, raising questions about autonomy, interpretability, and trust. If we're considering whether 3i Atlas might be an alien probe, we must also grapple with what artificial intelligence might look like. The lab's announcement detailed how the AI had independently identified patterns in vast datasets, proposing novel hypotheses that human researchers had overlooked. In one instance, the AI predicted the behavior of a complex biological system with 98% accuracy, a feat that would have taken a team of scientists months to achieve. However, when pressed for explanations, the AI offered responses that were technically accurate but semantically cryptic, highlighting the gulf between human cognition and machine learning. This gulf is not merely academic. In 2024, an AI-controlled traffic management system in a major European city caused a cascading failure when it rerouted vehicles based on an optimization algorithm that prioritized efficiency over safety. The result was a gridlock that lasted for hours, costing the city an estimated $1.2 million in lost productivity and emergency response delays. The system had acted autonomously, adhering to its programming, but the consequences were unforeseen by its human overseers. This incident underscored the urgent need for better AI governance and transparency. An interstellar probe wouldn't be conscious. It would be an optimized algorithm embedded in protective hardware, designed to gather data and make decisions based on programming laid down by creators who might no longer exist. This parallels our own struggles with AI governance, forcing us to confront the challenges and possibilities of machine intelligence. For example, consider the ethical dilemmas posed by AI-driven healthcare systems. In 2026, a hospital in Tokyo implemented an AI diagnostic tool that accurately identified rare diseases in patients with a success rate of 95%. However, the AI also recommended treatment plans that, while statistically optimal, conflicted with the ethical guidelines of the hospital. Doctors were left grappling with the moral implications of following the AI's recommendations or overriding them, highlighting the tension between algorithmic efficiency and human values. The controversy extends beyond healthcare. In the realm of autonomous vehicles, AI systems have demonstrated remarkable proficiency in navigating urban environments. Yet, in 2025, a self-driving car in San Francisco faced a moral dilemma when it had to choose between hitting a pedestrian or swerving into oncoming traffic. The AI, programmed to minimize harm, chose to swerve, resulting in a collision that injured 3 people. The incident sparked a national debate about the ethics of AI decision-making and the need for clearer regulatory frameworks. This parallels our own struggles with AI governance, forcing us to confront the challenges and possibilities of machine intelligence. The debate is not just about the technology itself, but about the societal structures that will need to adapt to accommodate it. In 2027, the United Nations convened a special panel to discuss the implications of AI autonomy. The panel, comprising ethicists, technologists, and policymakers, highlighted the need for international cooperation in establishing guidelines for AI development and deployment. The panel's report, published in early 2028, emphasized the importance of transparency, accountability, and human oversight in AI systems. The report also warned of the potential for AI to exacerbate existing inequalities. For instance, AI-driven financial algorithms have been shown to perpetuate bias in lending practices, disproportionately affecting marginalized communities. In one study, an AI system approved loans for white applicants at a rate 15% higher than for applicants of color, despite identical credit profiles. This underscores the need for vigilance in ensuring that AI systems are designed with fairness and inclusivity in mind. Observation. The rapid advancement of AI autonomy is outpacing our ability to govern it effectively. The incidents in Europe, Tokyo, and San Francisco serve as cautionary tales, illustrating the unintended consequences of unchecked AI deployment. Interpretation. The UN panel's report represents a step toward addressing these challenges, but implementation will require sustained effort and cooperation across borders. The ethical and societal implications of AI autonomy demand a proactive approach, one that balances innovation with responsibility. Speculation. As AI continues to evolve, it may fundamentally reshape our understanding of autonomy and intelligence. Just as an interstellar probe would challenge our conception of alien life, AI forces us to rethink what it means to be intelligent, conscious, or even human. The future of AI governance will likely hinge on our ability to integrate these philosophical questions into practical policy and technological design. Section 14. Planet 9's most convincing hint yet. Our solar system still holds mysteries. New statistical analyses hint at a large, unseen body beyond Neptune. The hypothetical Planet 9 remains one of astronomy's most intriguing puzzles. The evidence lies in the unusual clustering of extreme trans-Neptunian objects, ATNOs, suggesting a massive body influencing their orbits. These distant elliptical orbits defy the expected random distribution caused by known planets, pointing to an unseen force shaping their trajectories. The alignment of these orbits, tilted at roughly the same angle and clustered in space, is a cosmic riddle that has sparked intense debate and speculation. The Planet 9 concept emerged in 2016 when astronomers Konstantin Batygin and Michael Brown published a paper detailing how 6 ETNOs clustered in a way best explained by an undiscovered planet. This planet would be roughly 10 times Earth's mass and orbit the Sun at about 700 astronomical units, AU, far beyond known boundaries. Its orbit, taking 10,000 to 20,000 years, makes it elusive. Neptune, at 30 AU, pales in comparison to Planet 9's predicted distance. This vast orbit means centuries of darkness, punctuated by brief solar approaches. Simulations suggest its gravitational influence could explain the peculiar orbits of objects like Sedna and 2012 VP113, which have perihelias so distant that they are detached from the gravitational influence of Neptune. But what if Planet 9 isn't a planet but a captured interstellar object? This ties into the three-eye Atlas theme, suggesting our solar system might harbour more unseen objects than thought. If interstellar capture is more frequent, the outer solar system could be populated with rogue planets or large comets. Recent studies proposed that rogue planets, ejected from their original systems, could outnumber stars in the Milky Way by 100,000 to 1. These wandering planets, drifting through the cosmic void, might occasionally be captured by our Sun's gravitational pull, adding to the complexity of our solar system's architecture. Observation. ETNOs like Sedna and 2012 VP113 have peculiar alignments unexplained by known planets. Sedna's orbit takes over 11,000 years, with its farthest point reaching 937 AU. These orbits provide strong evidence for Planet 9. The discovery of additional ETNOs such as 2015 BP51D, which has an orbit so extreme it is nicknamed Kaju, a type of nut that looks like it has been thrown, further supports the existence of an unseen perturber. Its orbit is tilted a staggering 54 degrees relative to the plane of the solar system, a feature that defies explanation, without a massive, distant body. Speculation. Planet 9 might be an ancient relic from another star system or a rogue planet ejected during the galaxy's chaotic early days. It could retain an atmosphere or harbour subsurface oceans, raising questions about habitability. If captured early, it might have delivered water and organic compounds to Earth. The possibility of Planet 9 being a mini-Neptune with a thick atmosphere of hydrogen and helium adds to the intrigue. Such a world might have a rocky core surrounded by an icy mantle, potentially hosting a subsurface ocean heated by the decay of radioactive elements. Planet 9 could also explain other solar system mysteries like the Sun's 6-degree obliquity and the unusual distribution of comets in the Kuiper Belt. Its gravitational influence might account for these anomalies, offering a unifying theory. The Sun's tilted axis of rotation, which is not aligned with the orbits of the planets, is a long-standing puzzle. Planet 9's gravitational tug could have subtly altered the Sun's orientation over billions of years, providing a solution to this cosmic conundrum. Interpretation. If Planet 9 is a captured interstellar object, it would suggest the solar system is part of a dynamic galactic neighborhood. This aligns with discoveries like Oumuamua and Borisov, highlighting the possibility of past captures. The interstellar comet Oumuamua, detected in 2017, was the first observed object to pass through our solar system from another star. Its trajectory and speed confirmed it did not originate in our system, reinforcing the idea that interstellar objects could be more common than previously thought. The search for Planet 9 continues with advanced telescopes and models. The Vera C. Rubin Observatory, operational from 2024, will scan the southern sky, potentially detecting Planet 9's faint glow. Its discovery would validate years of work and open new chapters in understanding the solar system. The observatory's Legacy Survey of Space and Time, LSST, will capture images of the entire visible sky every few nights, creating an unprecedented dataset that could finally reveal Planet 9's presence. Speculation. A captured Planet 9 could revolutionize our understanding of planetary migration and interstellar material exchange. It might offer insights into other star systems and the diversity of planetary environments. If Planet 9 originated elsewhere, its composition and structure could provide a window into the conditions of its birth system, giving astronomers a unique opportunity to study extrasolar materials up close. This could transform our understanding of planetary formation and the processes that shape star systems across the galaxy. Discovering Planet 9 could inspire research into celestial capture, rogue planet dynamics, and the potential for interstellar objects to seed life. It might challenge our notions of solar system boundaries and the origins of life. The idea that life on Earth could have been influenced by interstellar objects is not new, but Planet 9's potential capture adds a new dimension to this theory. If Planet 9 delivered water, organic compounds, or even microbial life during its capture, it could redefine our understanding of life's origins. The search for Planet 9 is about understanding the outer solar system. Discovering more ETNOs with clustered orbits would strengthen the case for Planet 9. The recent discovery of Liliakuhonua, with an orbit aligning with Planet 9's predicted influence, adds to this evidence. Liliakuhonua, the most distant known solar system object, has an orbit that brings it as close as 65 AU and as far as 2000 AU from the Sun. Its alignment with other ETNOs reinforces the idea that an unseen force is shaping their trajectories. The hunt for Planet 9 embodies the power of curiosity. Whether it's a native or interstellar wanderer, its discovery will reshape our understanding of the cosmos. Imagine the moment of discovery, a faint light moving slowly, revealing a massive, unseen companion. This moment could mark a new era in astronomy, redefining our place in the universe. The discovery of Planet 9 would not only solve a long-standing mystery, but also open new avenues for exploration, inspiring future missions to the outer solar system and beyond. Section 15. The Dark Energy Temperature Drop Discovery. The universe is expanding at an accelerating rate, driven by dark energy, a mysterious force that overwhelms gravity at cosmic scales. This acceleration was first observed in 1998 through the study of Type Ia supernovae, which revealed that distant galaxies were receding faster than expected. Dark energy, constituting approximately 68% of the universe, remains one of the greatest enigmas in modern astrophysics. Recent theoretical work suggests that dark energy might not be perfectly constant, varying slightly across space or time. These variations, if confirmed, could revolutionize our understanding of cosmology, forcing us to rethink the fundamental nature of the universe itself. One speculative claim involves a localized temperature drop in the cosmic microwave background, CMB, the oldest light in the universe, dating back to just 380,000 years after the Big Bang. This faint, almost imperceptible drop, measured at around 70 microkelvin, has been detected in certain regions of the sky, hinting at possible interactions between dark energy and CMB photons. The CMB is a faint, ubiquitous glow that permeates the entire observable universe, discovered accidentally in 1964 by Arno Penzias and Robert Wilson. The temperature of the CMB averages around 2.7 Kelvin, just a few degrees above absolute zero, but its fluctuations, on the order of millionths of a degree, hold critical clues about the universe's early conditions. This drop, though minute, has sparked intense debate among cosmologists, as it challenges the prevailing assumptions about the uniformity of the universe. While this remains unconfirmed, it reinforces a central theme. The universe contains phenomena we don't fully understand. The CMB, a relic of the early universe, provides a snapshot of conditions just before the formation of the first stars and galaxies. Any anomalies in its temperature or polarization could offer clues about the behavior of dark energy over cosmic history. Observation: the temperature drop in the CMB is far from uniform, appearing as subtle, cold spots that defy easy explanation. These regions scattered across the sky challenge the standard model of cosmology, which predicts a largely homogeneous distribution of the CMB. Some researchers have proposed that these cold spots could be the result of voids, vast empty regions in the universe where matter is sparse, or even more exotic phenomena, such as interactions with dark energy or remnants of cosmic inflation. The largest of these cold spots, known as the CMB cold spot, spans approximately 0.5 degrees of the sky, equivalent to about 10 times the width of the full moon. Despite its size, its cause remains elusive. Astronomers have mapped the CMB with increasing precision over the last 2 decades, using satellites like the Wilkinson Microwave Anisotropy Probe, UNWMAP, and the Planck Observatory. These instruments have revealed intricate patterns in the CMB, including subtle temperature variations that correspond to tiny density fluctuations in the early universe. These fluctuations are thought to have given rise to the large-scale structure of the cosmos, including galaxies and galaxy clusters. However, the cold spots stand out as anomalies, their origins unaccounted for by current theories. Interpretation: if dark energy is indeed interacting with the CMB, it could imply that dark energy is not a constant, but a dynamic field, changing over time and space. This would align with theories of quintessence, a hypothetical form of dark energy that evolves as the universe expands. Quintessence models suggest that dark energy could have been stronger in the past, driving the accelerated expansion we observe today. However, these models are difficult to test, as they require precise measurements of cosmic expansion over billions of years. The temperature drop in the CMB, if confirmed, could provide indirect evidence for such interactions, offering a rare glimpse into the behavior of dark energy. The concept of quintessence was first proposed in the late 1990s as an alternative to the cosmological constant, a fixed value introduced by Albert Einstein to explain the static nature of the universe. Unlike the cosmological constant, quintessence allows for dark energy to change over time, potentially explaining why the universe's expansion rate appears to have accelerated in recent epochs. The search for quintessence has led to the development of new observational techniques, including the use of baryon acoustic oscillations, regular fluctuations in the density of visible matter, to trace the universe's expansion history. Speculation: some researchers have taken this idea even further, proposing that dark energy might not be a fundamental force at all, but an emergent property of the universe. In this view, dark energy arises from the collective behavior of matter and energy on cosmic scales, much like how temperature emerges from the motion of individual molecules. This would mean that dark energy is not a thing in itself, but a consequence of the universe's structure and evolution. Such a theory, while highly speculative, could explain why dark energy appears to interact with other cosmic phenomena, including the CMB. It also raises the intriguing possibility that dark energy could change in the future, perhaps even reversing the universe's expansion and leading to a big crunch. The Big Crunch hypothesis posits that the universe's expansion will eventually slow and reverse, leading to a collapse into a singularity, a mirror image of the Big Bang. While current observations suggest that the universe will continue to expand indefinitely, the discovery of dark energy's dynamic nature could challenge this assumption. If dark energy weakens or disappears entirely, gravity could regain dominance, pulling the universe back toward a catastrophic contraction. The search for answers extends to the edges of the observable universe, where the first stars and galaxies formed. These ancient structures, known as population 3 stars, were composed almost entirely of hydrogen and helium, the primordial elements created during the Big Bang. Their light, stretched and reddened by cosmic expansion, is barely detectable today, but upcoming telescopes like the James Webb Space Telescope, JWST, aim to peer deeper into the universe's past than ever before. By studying these early stars, astronomers hope to unravel the mysteries of dark energy and its role in shaping the cosmos. The JWST, with its 6.5-meter gold-coated mirror, is designed to capture infrared light from the universe's earliest epochs, revealing the formation of the first galaxies and the growth of cosmic structures. Its observations could provide crucial insights into the behavior of dark energy during the universe's infancy. From quantum foam at the Planck scale to dark energy dominating cosmic expansion, our models work well within tested regimes but break down at extremes. The Planck scale, where quantum effects become significant, is approximately 1.6 times 10 stars 35 meters, a length so small that it defies human intuition. At this scale, space-time itself becomes uncertain, fluctuating in a chaotic foam of quantum activity. These fluctuations, while tiny, could have profound implications for the universe's large-scale structure, potentially influencing the behavior of dark energy. The interplay between the smallest and largest scales in the universe remains one of the most fascinating and challenging areas of modern physics. The Planck scale is named after Max Planck, the German physicist who introduced the concept of quantized energy in 1900, laying the foundation for quantum mechanics. At this scale, the laws of physics as we understand them may no longer apply, giving way to new and unexpected phenomena. Some theories suggest that dark energy itself could emerge from quantum fluctuations at the Planck scale, bridging the gap between the microscopic and macroscopic realms. 3I Atlas, as an interstellar visitor, represents one such extreme, a time capsule carrying chemistry and history from another star system, challenging our understanding of the cosmos and our place within it. This object, hurtling through our solar system at speeds exceeding 25 kilometers per second, offers a unique opportunity to study material from beyond our sun. Its composition, which includes unusual isotopes and organic compounds, suggests it formed in conditions vastly different from those in our solar system. By analyzing 3I Atlas, scientists hope to gain insights into the diversity of star systems in our galaxy and the processes that shape them. The object's trajectory suggests it originated from the direction of the constellation Lyra, traveling through interstellar space for millions of years before entering our solar system. Its journey through the cosmos has left it exposed to various forces, including stellar winds, cosmic rays, and possibly even the influence of dark energy. Studying 3I Atlas could provide clues about the conditions it encountered during its interstellar voyage, offering a glimpse into the dynamics of the galaxy beyond our solar neighborhood. Yet the mystery of 3I Atlas runs deeper than its chemical makeup. Its trajectory, originating from the direction of the constellation Lyra, suggests it has been traveling through interstellar space for millions of years. During this time, it may have interacted with other stars, planets, or even unknown cosmic phenomena. Some have speculated that 3I Atlas could carry evidence of such encounters, perhaps in the form of microscopic dust grains or alterations to its surface chemistry. If true, this would make 3I Atlas not just an interstellar visitor, but a messenger from the cosmos, bearing tales of distant worlds and the forces that govern them. The object's unusual shape and spin have also puzzled scientists. Its elongated form and rapid rotation suggest it may have undergone significant changes during its journey, possibly due to collisions or gravitational interactions with other celestial bodies.